So I'm very happy to introduce Jamie Tucker-Foltz, who got his undergraduate degree from Amherst College, and so has been frequently seen at UMass, taking some courses. This is not the first theory seminar he's given. And then he got his master's degree supervised by Anuj Dawar, who's here today. And he's going to talk to, and he's a grad student at Harvard now, and he's going to talk to us today about unique games and inapproximability from a logical perspective. Jamie, please go ahead.
Cool. Thank you for the introduction. Everyone can see and hear me all right, right? Okay, great. So as I said in the abstract, this talk is going to be kind of a blend between two different worlds. The first world is classic complexity theory and where you're looking at optimal approximation algorithms and hardness of approximation. And the second world is descriptive complexity and logic, and how you can analyze restricted classes of algorithms by requiring that they be definable in a certain primitive logic. And so I'm going to be spending the first third half of this talk explaining the background on these two worlds and how they interact. And then the second part of the talk will be going through a sort of an extended proof by a few examples of how you actually prove things using this logical perspective, because it's possible to prove stronger statements than you could in classic complexity, where you often have to assume P is not equal to NP. If you make some restrictions, then you can prove unconditional statements on lower bounds. So diving right in, abstract definition we're going to need for a constraint satisfaction problem is specified by a set of variables and a set of constraints. And the object is to assign values to the variables satisfying the maximum number of constraints. Okay, so the complexity of a CSP is determined by what kinds of constraints are allowed. So, for example, and one that you may have heard of is 3SAT, where the variables take values either true or false, and every constraint asserts that a specific disjunction of three literals is true. Okay, so the kinds of constraints determine the complexity. This one, it's hard to even determine whether the optimal value is one or not, whether all constraints can be satisfied. Another CSP maybe is less familiar is unique games. So this is going to be the star of today's lecture. And it's parameterized by a positive integer q, which is called the size of the label set. And you have to assign values. The variables take values from 0 to q minus 1. And every constraint, the constraints are only between pairs of variables. So in 3SAT, you have constraints on triples of variables. But in unique games, they're only on pairs. And they have to be, then the constraints say that whatever values you assign those two variables have to be consistent with some permutation. So in other words, if I have a constraint between x1 and x2, and I have a value I'd like to assign to x1, then the constraint uniquely determines what's the corresponding value I should assign to x2. So it's probably easier to explain this through an example. So when the label set size is 2, there's only two permutations on the label set of 0 and 1. So there's only two kinds of constraints. The constraint that says two variables have to be the same, and the constraint that says two variables have to be different. And so you can represent this graphically, where I've got the 6 black dots are variables, and the edges are, the green edges are the things that are supposed to be the same as each other, and the red edges are the things that are supposed to be different as each other. This is going to be a running example that I'll keep coming back to. And by the way, if anything is remotely unclear, please just interrupt me. I'm not monitoring the chat, so I won't necessarily see questions there, but please do just interrupt at any time if anything's unclear. So in this instance, what's the optimal value? Well, in fact, if you stare at it, you can see the optimal value is 1, meaning 100% of the constraints can be satisfied, and it's by this assignment. So I'm assigning 0s and 1s to the variables, and you can check that wherever there's a green edge, they take the same value, and wherever there's a red edge, they take different values. So every constraint is satisfied by this assignment. So we say the optimal value of this unique games instance is 1. What about this one? So now what I've done here is I've changed the bottom 4 constraints. I've swapped the reds versus the greens. And so the same assignment will satisfy all except those constraints. But you see now we have problems like this 0, 1. You can see my cursor, right, when I'm moving this. Yeah, great. So this one is one that's not satisfied because I have a 0 here and a 1. They're supposed to be the same, but they're not the same. But this satisfies the other 2/3 of the constraint. So the optimal value is at least 2/3. And in fact, it's exactly 2/3. And have just a quick proof of that fact. Let's just look at this triangle of constraints here. Here, these two variables are supposed to be the same. These two variables are supposed to be the same. And these two are supposed to be different. So clearly that's inconsistent. I can't satisfy all three of those. So at most 2 out of those 3 constraints can be satisfied. And similarly, at most 2 out of 3 of these constraints, and these constraints, and these constraints can be satisfied, all for the same reasons. So the optimal value is 2/3 because that's all of the constraints. I just enumerated all the constraints. Okay, so I'm going to be looking at the problem of how do you compute the optimal value of a unique games instance, but not from the standard viewpoint of computational complexity, but from descriptive complexity. So I want to explain what this means. So to make an analogy, in ordinary complexity, we think of your problem instance being encoded on a tape, and then that encoding is given into a Turing machine, and the Turing machine either accepts or rejects in the end of its computation. Okay, so this is how we often think of computation. Descriptive complexity, if I was to make an analogy, you encode it differently, and instead of having a Turing machine solve the problem, you have a logical sentence solve the problem. So for unique games, how this encoding works is it's encoded as 2 things, a universe and a set of relations. So the universe for a unique games instance, or in general a CSP, will be the set of variables. And the relations are, you have one relation for each type of constraint. So here the S relation lists all the things that are supposed to be the same according to the constraints, and the D relation lists all the things that are supposed to be different. So because I have a green edge between A and D here, I put AD and DA, so by symmetry, into the S relation. And similarly, because I have a red edge between A and C, I put that into the D relation. Okay, so then we go and instead of having a Turing machine, we have some logical formula. And this is the analog, and it's of the form, there's for all quantifiers exist quantifiers, there's references to the special relation symbols. So whenever you see a for all or there exists, that means for all elements of the universe, which in this case is the set. So it's saying like, okay, so if I was to read the sentence, I'd say, okay, is it true that for all X in the universe, A, B, C, D, E, F, there exists some Y such that S holds of X and Y and some other stuff, ... Okay, so far that's true. For any X, there does exist a Y that has a green edge to it in this diagram. So given any logical formula and any instantiation in terms of these relation symbols and what the universe is, you can just go evaluate, is this formula true or not? And we think of that as analogous to the Turing machine accepting or rejecting. So in ordinary complexity, we ask questions like, what resources does M require? How much time does it take? How much space does it use? Does it use non-determinism, etc.? And in descriptive complexity, the analogous thing is what logic can we express such a formula expressing some property in? And there's a beautiful correspondence between computational resources and logical resources. So for example, take the class of polynomial space, P space, the problem solvable in polynomial space. Well, that corresponds exactly to those problems that are expressible in with a formula here in second order logic. Okay, so there's a nice correspondence between these two things, and just an alternative viewpoint. And there's one more thing you can do. So in classic complexity, we can think of not just Turing machines that either accept or reject, but do something like output something like a number. And the analog of this kind of input-output algorithm in descriptive complexity is what's called an interpretation. And for our purposes, roughly speaking, it takes as input not just the structure, but also an index of a certain bit. And it says whether that bit is 1 or 0. Okay, and so this mapping between bit indices to ones or zeros gives us a number that we say that like, so phi of A equals this number, defined by that mapping from bit indices to zeros and ones. Okay, does this make sense so far? And any questions? So I'm going to talk about a few specific logics now. So the most basic thing is first order logic, where you're just allowed to have, for all quantifiers, there exist quantifiers, and these are again over the universe, and the standard Boolean connectives, and of course the special relation symbols that are used to encode the problem. So there are problems that are solvable in polynomial time, but not expressible in first order logic. Okay, so there's these extensions of first order logic that have been proposed to try to capture more of polynomial time. And the first one is LFP, stands for least fixed point. Don't worry about what that means. And it's first order logic plus the ability to write inductive definitions. And you can inductively define relations. So a classic example is to say if the input's a graph and you want to know if the graph is connected or not. That's something you can't define in first order logic, but you can define it inductively by saying, is there a path from X to Y? Well, that's true if X equals Y, or Y is adjacent to some Z and there's a path from X to Z. And so that inductive definition of connectedness, that's something you can do in LFP that you can't do in first order logic. But that still doesn't capture all of polynomial time. And so there's another extension, which is called FPC, which stands for fixed point logic with counting. And this is the main logic I'm going to be focusing on today. And in FPC, you have all the power of LFP plus numeric variables and counting quantifiers. So you're allowed to say there exists exactly I elements in your universe that satisfy some property where I is a numeric variable. And this lets you compute even more, but it still does not capture all of P. But it's a very important class, as I hope to convince you of on the next slide. But just to give you an example of a good canonical problem that really needs the full power of FPC to solve is the problem of given a graph where you encode the vertex set is the universe and the edge set is a relation, is the graph Eulerian. So a graph is Eulerian, we know, if and only if it's connected and has no odd degree vertices. And to express these things, well, as I was just arguing, you need the ability to find inductive relations to express the fact that G is connected. And you need counting quantifiers to express that G has no odd degree vertices. So for example, here's what such a sentence for the Eulerianness property would look like. So I'm not going to go into detail how you would write this as a logical sentence. That's kind of beyond the scope, but I do want to explain what the counting quantifiers get you. So Eulerian if it's connected, and for all x, it is not the case that, and so this is, we want to mean x has odd degree. And so this says there exists I, there exists j, such that I plus 1 equals j, and this plus can also be done using inductive definitions. There's a way to formally define how you do this plus operation, but so don't worry about that. So this part here says that j is odd, essentially. If there exists I, exists j, such that I plus 1 equals j, and they're all assumed to be integers. And then there exists exactly j vertices y, such that there's an edge from x to y. All right. So this does express the fact that there's an odd number j such that there exists exactly j vertices y with an edge from x to y. In other words, x is odd degree. So that and this part here, there exists j y. This is a counting quantifier, and this is what you need FPC to do. So why do we care about FPC? Some people might say you don't care, and that's because.
Sorry, can I ask you a quick question?
Yes.
Is it obvious that all these things should be contained in or I guess they're not really contained in, but like any problem that you can express in these logics, you can solve in polynomial time? Or?
It's not obvious. I'd say it's straightforward to prove, though. Okay. Well, like first order logic, I can easily give you a proof right now. Basically, you have some finite sentence, and you just parse the sentence. If you hit a for all quantifier, you do a for loop over your universe. If you hit an existence quantifier, you do a for loop over your universe. And then in the end, you're just like, if the relations are just encoded on a Turing machine, the atomic things you do is check, okay, is that bit true, essentially?
Right. But it couldn't have it couldn't be that there's like some massive formula, like exponentially sized formula or something that expresses your polynomial sized problem, or?
So the logical formula is a finite thing. It's like a Turing machine encoding is finite. Right?
Yeah, I got it. Yeah, thanks. That makes a lot of sense.
Good question. Okay, so why do we care about FPC? So if you're one of the special relation symbols used to encode your problem, if it's just a total order over the universe, then P collapses to LFP. If you have a problem of this form, you can solve it in polynomial time, if and only if you can express it in LFP. So some people might say, LFP, we're done. That solves the problem. That logic exactly captures polynomial time. And this is a very famous result proved by someone in this audience. But if you don't have such a relation symbol that's a total order of the universe, this doesn't hold anymore. And in fact, even FPC still does not capture all of polynomial time. There are polynomial time computable properties that are not definable in FPC. And this is very non-trivial to establish. And this was, again, approved by someone in this audience, maybe the same person. What is FPC? We have some subset of polynomial time computation, and what does it correspond to? And philosophically, it can be argued that definability over FPC corresponds to solvability by a symmetric algorithm. And what is a symmetric algorithm? It's an algorithm where you're never allowed to make an arbitrary choice like, okay, I have some set, I have some collection, pick some arbitrary element from it. Even if it doesn't matter what element you pick, and the algorithm will always be correct no matter which element you pick, just making that choice in a way breaks the symmetry of your input problem. And so a classic example is Gaussian elimination. And so in the Gaussian elimination algorithm, one of the things you have to do is you have to repeatedly choose a pivot row. And if you so you can think of how you do this. Well, you normally think of a matrix as having ordered rows, right? And if we look at, this is the pseudocode from the Wikipedia page on how you do the Gaussian elimination algorithm, and you see this variable h here is like really explicitly using the fact that your columns and rows of your matrix are ordered, and it's resolving these issues of choosing an arbitrary element by saying take the smallest element. And so that's what you're allowed to do, even in LFP, with if you have an ordering relation. Essentially, it's the same basic idea. But if you have a structure encoded in a way that you don't have any natural sense of ordering, so you could encode matrices with an abstract set indexing the rows and columns, in which case you don't have this natural ordering, and then it's a symmetry breaking thing to choose an arbitrary pivot, and it doesn't make sense semantically in the logic that you could even do that. So FPC captures what you can do without making arbitrary choices, essentially. And you could think of how you do Gaussian elimination without choosing a pivot. Well, one thing you could do is try all pivots. That doesn't break symmetry, but that's going to lead to an exponential time algorithm because you have to choose a pivot at every step, so it's exponential time. So that's philosophically what FPC corresponds to. And it's a really robust class, even despite this inability to do this task of Gaussian elimination. It can find the optimal value of a linear program or a semi-definite program. So it's a very important piece of P, and it's very interesting to study just on its own right. And any questions before I move on to the technical stuff? This is just motivating the background. So I'm going to look at what you can do in FPC. That's the theme of today's lecture. And by restricting attention from what you can do in polynomial time to what you can do symmetrically, meaning by an FPC definable algorithm, which I'll define formally in a bit, you can actually prove some lower bounds, like you can't do this, you can't do that. So the last ingredient is approximation. And so for any alpha in 0, 1, an alpha approximation algorithm is a polynomial time algorithm where if I give you an instance of optimal value of x star, it'll give you some approximation of x star in the sense that x has to be at least alpha x star, but can't be more than x star. So you're never allowed to overshoot, and it has to be within alpha of the optimal. So this is for a maximization problem. And there's this, there's this theory of approximation algorithms. What's the best alpha you can get? Closer to 1. If you get alpha equals 1, that means you're exactly solving the problem. And there's this big conjecture in the theory of approximation algorithms called the unique games conjecture that essentially says unique games is very hard to approximate. And it's that for all epsilon delta greater than 0, for a large enough label set Q, it's NP hard to distinguish unique games instances on a label set of size Q that have really high optimal value and have really low optimal value. Okay, so if you had an alpha approximation algorithm for a constant alpha, then for small enough to epsilon delta, you could distinguish these two cases. Because you basically say, oh, okay, if I get a really high value, I know I'm not in this case. And if I get a really low value, I know I'm not in this case. So this implies that there's no constant factor approximation for unique games. It's actually quite stronger than that. It's saying like, so gap problems like this are called gap problems. You're given an instance with the promise that it's a really high value or a really low value. You have to determine which it is. And the hardness of a gap problem implies hardness of approximation, not necessarily the other way around. And there's this beautiful theorem that characterizes the best approximation algorithm for any constraint satisfaction problem in a very abstract sort of way. And it says that if you assume the unique games conjecture and P is not equal to NP, then the best approximation algorithm for any CSP is given by the specific semi-definite program. And this is proved by a reduction from this unique games gap problem to your arbitrary CSP optimization problem. You can transfer the gap, this gap into another gap. So one thing I wonder is how does this translate if we were to impose the requirement that your algorithm be symmetric, in other words, definable in FPC. So we can, instead of requiring an alpha approximation algorithm, we want an FPC definable alpha approximation algorithm. And so this is just going to be an FPC interpretation, as I defined it earlier, with the same exact guarantee. Okay, that gives you a good approximation of the optimal value. And then we can define an analogous FPC unique games conjecture, where for any epsilon greater than 0, same thing, instead of having a polynomial time algorithm distinguishing these two cases, we say that we conjecture that there is no sentence of FPC distinguishing these two cases, in the sense that if your input satisfies phi, it should have high optimal value, and if it does not satisfy phi, it should have low optimal value. Okay, so a single sentence distinguishing these two cases. And then we get the following theorem. If you assume the FPC unique games conjecture, then the best FPC definable approximation algorithm is given by exactly Raghavendra's semi-definite programming relaxation. And so this proof roughly goes by just checking a few kind of tedious things. It's that, first of all, the semi-definite programming relaxation can actually be solved in FPC. And secondly, that this reduction from unique games can be defined in FPC. So everything just goes, there's nothing unexpected that happens. But notice one interesting thing is that we've removed an assumption that P is not equal to NP here. In classic complexity, to prove it's hopeless to even try proving there is no polynomial time algorithm that distinguishes these two cases. It's just, you can't say something like that. The best thing you can say is it's NP hard. But in descriptive complexity, it sometimes is possible. And for FPC, it is possible to show that there are things that cannot be expressed in FPC. So cannot be solved, unconditionally cannot be solved by a polynomial time algorithm. And so I'm going to spend the rest of the talk explaining how you prove something like that by going through an example using unique games. We're not actually going to prove the unique games conjecture. I wish I had a proof of this, but it's an elusive problem, even if you require FPC definability. But we are going to get a statement of this form, where we're going to have a worse gap, and it's not going to be 1 minus epsilon delta. It will be something weaker than that. But it is still nevertheless a very non-trivial result. And so that's the rest of the talk is going to be about that. But any questions about the background or
yes,
this theorem?
I have a question, Jamie. So in the theorem, you stated this as solving and rounding a specific program by analogy with what Raghavendra is. But I'm wondering whether you mean rounding. So do you actually round semi-definite programs, or do you just look at the optimal value of the semi-definite program?
Right. Yeah, I think you just look at the optimal value. Right. The rounding is only to give you an actual instance realizing that, but you can't actually do that without breaking symmetry. So yeah, good point. Yeah, you just get the optimal value. That's all you can really do. Any other questions?
Yeah, have you found like any?
Sorry, am I making noise?
Oh, I think someone is. I don't know if it's you.
I think it's me.
Oh. Yeah, I was wondering if you'd looked at sort of all cases in which the SDP relaxation is the best, like if there are things that aren't FPC definable where the SDP relaxation is still optimal, or if FPC definable is really the biggest class of.
Sorry, it might be because of this ringing. I had trouble understanding your question. It's done now. Sorry.
Okay, yeah. I was wondering whether in what case the SDP relaxation is the best, if you've thought about that, and if there are any algorithms that aren't like.
I mean, we don't have any algorithms that beat it. And most people, I think, believe this conjecture and believe this theorem that it is the best. Yeah, that's all I'll say.
Okay.
Are there what are the known? I guess this is more kind of a unique games conjecture kind of thing. But what are known dependencies of Q on epsilon and delta? Like, do we know that Q has to be at least this sort of a function of?
Yes, there are known dependencies. I do not know them off the top of my head. So sorry. Yeah. But yeah. Okay, so I really want to have enough time for the fun part of this talk, which is let's prove some FPC lower bounds now. Okay. I need to prove a statement of this form. CK. And what CK is first order logic with you're allowed counting quantifiers as well, but instead of inductive definitions, you're allowed to just write down infinitely long sentences. So you can unroll your inductive definition into an infinitely long sentence, and it will not take up. It will still only take up a finite number of variables. Okay, so because you start with a finite sentence in the FPC, because FPC only has finite sentences, you're only going to get a finite number of variables. Okay. And so we're going to use this fact that there's a finite number of variables to get a contradiction. And explicitly what we're going to do is exhibit two instances, AK and BK, such that A has high optimal value, B has low optimal value, but it's impossible for any sentence to evaluate to true on one and false on the other. They're CK equivalents. No sentence of FPC, no sentence of CK, sorry, can distinguish A from B. So clearly this gives you the contradiction because we're assuming that phi does distinguish these two cases, high optimal value from low optimal value, but they can't distinguish them because they're CK equivalent. And so proving this third part's the hard part here. And for this, we use a nice characterization of CK equivalence in terms of a game between two players. It's called the K-Pebble bijective game. If you're looking at this picture, this game is not in stock. It's a made up. No one ever sold a board game called this. It's a doctored image, but it's a game between, on the left, the son here, spoiler, wants to prove that A and B are non-isomorphic, and the dad, duplicator, wants to pretend that they're the same. And what they're going to do is that they're going to place pairs of pebbles on the board, one in each structure, on the elements of the universe. And if you ever get a relation that holds between some pair of pebbles in one structure but doesn't hold between other structures, then spoiler wins. And I'll go through the exact rules of this game on the next slide. We're going to go through an extended example. But the upshot is, if A and B are CK equivalent, if and only if duplicator wins the K-Pebble bijective game between A and B. And so the pebbles kind of represent the variables in your sentence. Okay, so let's play the K-Pebble bijective game. It turns out this pair of instances, which are not the same, they have different optimal values as we saw, they are nevertheless C2 equivalent. So we will show that duplicator has a winning strategy in the two-pebble bijective game, so there's two pairs of pebbles. So how the game goes is every round, spoiler picks up one of the pairs of pebbles. And then duplicator is asked to write down a bijection between the universes of the two structures. So in this first step, they're going to be able to get away with just writing down this nice identity-like bijection. And then spoiler puts the pebble pairs down, one pebble on each structure respecting this bijection. Okay, they could choose any one of these 6 pairings to place the pebbles down on. And then we check, are there relations that hold in one structure just among the pebbled elements that don't hold in the other structure? And so far, we're good, because there's only one pebble and the relations have 2 variables in them. Okay, so then we keep playing over and over again. So let's say spoiler picks up this pair of pebbles again. In this case, duplicator can still respond with the same identity bijection. And you can see, by the way, here that if A and B are really the same, they're isomorphic, duplicator can just always give this isomorphism between them and win the game. So it's really it's a weaker notion of equality. And so say spoiler picks this pair, and then we check and we see, okay, there's a green line here and there's a green line here. Spoiler would win if there was like a green line here and a red line here or no line here. Okay, so duplicator is still good. But now it gets interesting. So let's do one more round. And suppose spoiler picks up this pair of pebbles again. Now we could be in trouble if we gave the identity bijection, because there's it's a red line here and a green line here. So if spoiler puts the pebbles here and here, then spoiler is going to win. So what duplicator does instead is they swap these two. Okay, and now you can check, no matter which of these pairs spoiler puts the pebbles down on, duplicator is going to be fine. You'll get the same color relation no matter what. And I'm not going to go through the details of how this is cooked up. I'll present the general construction from which it's derived in a moment. But you can play this game ad infinitum and spoiler will never win. And it gets a bit more tricky now that we've got these two that are crossed. So if we go another round, spoiler picks up this pair of pebbles. Now, because these two are crossed, these two have to be crossed as well. But you can keep playing this game and check that there's no way that spoiler can ever win using this strategy. So what we've just shown is that I claim we've just assembled all the ingredients to prove this very weak proposition here that says for any alpha greater than 2/3, there's no C2 definable alpha approximation algorithm for unique games on a label set of size 2. Okay, so how does this go? Well, what did we just show? We just showed that A and B that we constructed are such that A has optimal value 1, B has optimal value 2/3. We showed this right at the beginning of my talk, and they're C2 equivalent. Okay, because duplicator wins on the game between A and B. So using these first two conditions, suppose you do have some interpretation, a C2 interpretation that takes as input unique games on a label set of two sides to structure and outputs a number, and it gives you an alpha approximation. Well, what does that mean is that phi of A should be at least alpha times the optimal value of A, which is alpha, because the optimal value is 1. And phi of B, another condition of being an approximation algorithm, is that you don't overshoot. So phi of B is at most the optimal value of B, which is 2/3. And then we use the fact that they're C2 equivalent to say that whatever number this interpretation outputs, it must be the same on both structures because you can't distinguish them in C2. So if we read all these equations from here to here, we get that alpha is less than or equal to 2/3 QED. So what we want to do now is we want to do this argument not just for C2, but for any CK. And that will give us the result we want, because what we really care about is the logic FPC. We want to show that there's no FPC interpretation. And because FPC is contained in the union of all of these CK classes, we just have to do this for an arbitrary K. We don't know which K your FPC sentence is going to land in, so we need to do a proof like this for an arbitrary K. And I'll note that there's a fundamental challenge we hit when K is at least 3, and that's that we can't put a 1 here. Okay, so it is possible to write down an FPC sentence with 3 variables or a C3 sentence that distinguishes optimal value 1 from optimal value less than 1. So if you have a 1 here and K is at least 3, you're never going to be able to prove CK equivalence because there is a winning strategy for spoiler. So we're going to have to make some sacrifices on the optimal value of this one. And this is by the way, this corresponds to the fact that it's easy in polynomial time to determine whether the optimal value of a unique games instance is 1 or not. There's a very simple algorithm and there's a very simple logical sentence that does that too. Okay, so we're doing so the main theorem is that for any delta greater than 0 and for any positive integer L, we can construct a sequence of unique games instances AK and BK on a fixed domain, so for some fixed Q, such that for all K, the optimal value of AK is very high, and very high depends on L, and the optimal value of BK is very low. It's not very high and very low. I'll plug in some values of L to show you exactly what this shows. And their CK equivalent is the last thing we want. So this is like unique games. If I could put a 1 minus epsilon and a delta here, we would have proved the FPC unique games conjecture. And so a corollary, if we plug in L equals 1, what this means is that for any delta greater than 0, there exists a Q such that no sentence of FPC distinguishes unique games instances that have optimal value at least a half from those with optimal value at most a third plus delta. Okay, so that's just plugging in. You get a half here when you plug in L equals 1, you get a third plus delta here. Okay, and so if you were to apply the same logic as we did on the last slide, that shows that for any alpha greater than 2/3, there's no alpha approximation algorithm for unique games definable as an FPC interpretation. So before we had a 1 here and a 2/3 here, and now we have a 1/2 and a 1/3. But all that matters is the ratio. You still get the same result that there's no 2/3 or better approximation algorithm. And in fact, you can do even better, because if you send L to infinity, the ratio becomes arbitrarily small. So you can prove that for any alpha greater than 0, there's no constant factor approximation algorithm for unique games definable as an FPC interpretation. So there's no symmetric algorithm to solve unique games with up to any approximation ratio. I'll just note that statements like this are what we ultimately care about in the theory of approximation algorithms. We want to say we want to characterize what is the best approximation ratio you can get. But statements like this are more useful to work with. Giving an explicit gap of saying it's hard to distinguish instances of this value from this value. That's like a more useful result, because you can use reductions to transfer that gap to get gaps for other problems. So in fact, well, this sounds like a better result. This was actually the harder one to prove. And so that's why, yeah, it's an interesting result on its own. So I'm going to go through the k equals 3 example. And I'm going to explain the general construction and then go through a bit more detail of k equals 3 example to show what's involved, because k equals 3 is where it really becomes harder. Any questions before I go into it? Okay, so here's the construction of AK and BK. They're CK equivalents. It's AK has a large optimal value and BK has a low optimal value. So we're going to let L and K be given. These are parameters of the construction. And then we're going to choose positive integers, R really great, really huge, and then M mediumly huge, and then L. And then we're going to take some graph, and it has to have a high degree and a high girth. And so girth, for those of you who don't know, it's the length of the smallest cycle in the graph. And the degree has to be exactly this 2L plus 1 to make this work. That's a very critical value. And then for any edge in the graph, we're going to associate that edge with a random vector from this vector space F2M. So this is the m-dimensional vector space over the finite field of 2 elements. In other words, binary strings of length m under bitwise XOR as the operation. And so we're going to write down a random vector on every edge and a random L-dimensional subspace on every edge. Okay? Yeah.
How do you know that you is that like, oh, that's like Euler or someone, right? Like, oh, how do you know that H exists?
Yeah, there are constructions of you give me any degree and any girth. There's a graph of that degree and that girth. Okay, cool. Yeah, it's not trivial to prove. It's a fun exercise to try to think how you would construct these. They're really, really hard, and they're exponentially huge. So R is a huge number, and then this graph is even huger. It's like embarrassingly big. How big these instances have to be. Okay. Next step, and so this is the most technical part, the key ingredient that makes everything work, is that we're going to throw out some edges from from H. So an edge is a bad edge if you've got some path that starts at that edge of length at least R, such that if you look at all the vectors in the subspaces along that edge, as you traverse the path, those vectors do not span the vector space. Okay, so any time you have an edge and a path of length R, where if I collect all the vectors I've encountered along all the subspaces along that path, it doesn't span the vector space, I throw the edge out. And you can prove because it's how the numbers are chosen that there's going to be very few edges that you throw out in this step. You're never able to eliminate them, but there's very few of them, so it doesn't have a huge effect. But you don't want edges with this property. It's going to make it hard for duplicator to win. Okay, so then so then I need to tell you how I'm defining A and B. Okay, all I've defined is this graph and these subspaces. So the variable set is going to be the vertices of the graph cross the vector space. So and I'm going to write these as indexed by using this standard notation from literature. I know some people here wrote papers using the same notation, where you have the vertex subscript in the bottom, and the vector is the G here. So these correspond to the variables, and the domain is the vector space. So you want to assign values to the variables, and each value of the variable has to be a vector in this vector space. Okay, so what are the constraints? For any V1 and V2 and the adjacent edges in the graph, and any G1 and G2 in the vector space, and any Z in the subspace on the edge between V1 and V2, I'm going to add the following constraints. In F2, it's going to be X V1 G1 minus X V2 G2 equals this. And in B, same thing, except I also add this random vectoring. And so the good thing to check is, are these really valid unique games constraints? Okay, right, a unique games constraint has to be between only two variables, true, and it has to be such that if I give you the value of one, it uniquely determines the other, true, again, by just algebra, it's a group, the addition operation here. And so if you stare at this, it's not too hard to see, you can exactly compute what the optimal value of A is, and it's 1/2 to the L. And that's from the fact that you can always satisfy the Z equals 0 constraint by setting XV1G1 to be G1 and XV2G2 to be G2. I think some of these pluses should really be minuses, but it doesn't matter in this group because plus equals minus. But so you can prove that the optimal value, that's just some tedious analysis to show that the optimal value of B is probably very low, but it all goes through. The interesting part is how do you show that these are CK equivalent? So that's what I'm going to do the example now. So in fact, the example I went through last time with where the graph was K3, and we showed this 1 2/3 gap. So that's kind of the special case when L equals 0 in this construction. And so now I'm going to do the special case where L equals 1. So in other words, the vector space, we have M equals 2. So the vector space consists of binary strings of length 2. So like this is an element, for example. And L equals 1. So I've got a one-dimensional subspace along each edge. And the graph here is K4, a complete graph on 4 vertices. And so on every edge, I'm listing what are the subspaces. So this is the A instance, this is the B instance. And the only place where they differ is on this bottom edge where I've added a random vector, B, shifting this subspace 0, 0, 0, 1 into an affine subspace 1, 0, 1, 1. Okay, and that's what it's doing if you look at the constraints. So just to give an example, how to read this diagram, the constraints involving these two variables, x1, 0, 0 and x2, 1, 1. Well, I look at, okay, vertex 1, vertex 2 in the graph. I'm just looking at the left instance right now. And I see, okay, I've got a 0, 0 here and a 0, 1 here, and that corresponds to this 0, 0 and this 0, 1. So I add all the vectors along the subspace plus the things in the superscripts, and I'm just simplifying what these add up to in this vector space. So this is how to read these equations. And don't worry if you don't understand all the details. This is going to start becoming less and less intelligible in a moment. I just want to convey some key ideas of the general ideas of how this works. But so this is an example instance that are going to be C3 equivalent. And so how do we show this? So suppose we're playing our K-pebble bijective game, and as we go, we start out as before. We're going to give the identity bijection between the two structures until we get to a point where I've got a pebble pair placed on somewhere where I've got the inconsistency. So I've put these in red because this is where the two structures differ. I have different constraints between these variables as between these variables. So now if spoilers just picked up the third pebble pair, I have to worry if I give the identity bijection again, if they place it anywhere among the X3 guys, duplicator is going to lose. So what I have to do now is give a slightly different bijection. And the bijection is going to be of the following form. I'm going to permute just with the X3 guys and by adding some elements. So I'm going to send any X3A to X3A plus B. This is going to be a bijection by group theory. And then I have to say, okay, I'm just trying to solve for B. What should B be? And if you look at the constraints, you'll see that if I want to have partial isomorphism over this edge and this edge, okay, between the things involving the X3 variables and the X1 variables, B has got to be either 0, 0 or 1, 0. And this corresponds to the fact that I've got a 0, 0 and a 1, 0 here. Okay, so you can just, I'm not going to justify any of these claims I'm making. It is the case that this bijection will give you consistency between the two structures. Duplicator won't win because of a problem between the pebble pair here and here if they place it here, as long as B is either 0, 0 or 1, 0. And then if I want to make a consistency across this bottom edge, B has to be either 1, 0 or 1, 1. So hey, it looks like I'm in luck. If I choose B to be 1, 0, it makes both of these consistent. And the general reason why, so I put a 1, 0 here. The general reason why this works is linear algebra. It boils down to solving a system of two equations with two unknowns. And so there is a choice that will make this path of length 2 from x1 to x3 to x4. It'll make all of these guys consistent. And by applying this permutation, if I was actually to redraw this figure with this permutation in mind, putting the variables in the corresponding places, what I've essentially done is I've moved the inconsistency from this bottom edge to this edge over here. And this is great because now I don't have a pebble that's on a red spot. So if the duplicator spoiler only wins if they get a pebble pair with red where there's the inconsistency, and they will get a pebble on each side. So I've got two pebble pairs already on the board. I've now made those green, and I've moved the inconsistency to where there's no pebbles. So no matter where spoiler puts the pebbles, duplicator is going to be okay. Okay, and this is where they would do it if they chose to have x3, 0, 0 on the left structure. And so you can repeat this. So if spoiler picks up this pebble pair, now it's time to move the inconsistency from this edge to this edge. And we do that by applying a permutation to the variables here. And we just, again, compute what makes this consistent, what makes this consistent. And it turns out to, again, be 1, 0, kind of by coincidence in this case. And so you just keep track of all the existing group elements you've added to each of the vertices, and you use those to derive what the new ones must be. And you can show that you can repeat the strategy over and over, and duplicator will never win in this. Spoiler will never win, so duplicator wins, so they're C3 equivalent. So far, this is all a lot of magic. I'm not going to reveal exactly how all of this stuff works because it's very technical. But I do want to just give a little more intuition and how this step 5 is useful. And step 5 is really the key in this general construction that makes this whole thing work. And it's by this following lemma. So say I have a path in your graph from V0 to Vn, and n is greater than or equal to r. So the path has at least r edges in it. And if I'm given any values in the vector space for g star of V0 and g star of Vn, we can extend g star to be a map over the entire path between V0 and Vn, such that the map that sends xvg to xvg plus g star of V is a partial isomorphism between A and B over the set of variables involved in that path. Okay, so what this looks like in the picture, in this case, R was like 2. What we wanted to do when at this first step, when duplicator was at first defining this bijection here, is we want to find some g star of 3 value to add to make this path consistent with this path. And the structures look the same over these two paths. And it just so works out that because I've thrown out any bad edges, if I look at and this path is at least length r, that means if I look at all the vector spaces along this path, look at this, I have 0, 0, 1, 0, 0, 0, 1, 0, 1. Okay, 1, 0, and 0, 1 are linearly independent. So because by the fact that this 1, 0 and the 0, 1 are choices that I have, I can use the fact that this spans the vector space to show that I can make this path consistent. Okay, so that's the fundamental reason we throw out the bad edges, is I want, anytime I've got a path of length r, I want to be able to find intermediate values of this form so that a permutation of this form will make the two structures look the same over that path. So how does this help duplicator in general? Well, duplicator's general strategy in your graph, and this is, again, looks way too small here. This doesn't actually correspond to a real instance I've cooked up, but I was trying to show the main idea, is that duplicator is going to maintain consistency over a minimal spanning tree between all the pebbled vertices. So anywhere I've got pebbles, I compute what's the minimal spanning tree, and I want each round duplicator is maintaining an invariant that the structures look the same over this minimal spanning tree. So the nice thing is that if spoiler puts more pebbles and grows the tree slightly, it's always possible to make neighboring vertices consistent with whatever permutation I had going on here and here. I make a permutation from here to here to make the neighboring guys consistent. And so when the tree changes by just a little bit, I can keep this invariant. And so say we keep going, lifts this pebble up, puts it there, etc. The only thing I have to worry about is when the tree changes substantially. So when I've crossed over here, now I've got this new path and now I've got things that I need to make consistent with these pebbles and with these pebbles simultaneously. Now that's not always possible, but now we use the fact that the girth was chosen to be very large. So if the girth was very large, then it means that anytime the tree changes in a substantial way like this, it means that I've got a really long path that I need to make consistent. And specifically, the bound on the girth is related to r, and it's going to ensure that this new path is going to have length at least r, so we can apply this lemma and use it to make this path consistent. Okay, that's the main idea behind this construction. Any questions about this? I'm about done now. I'll just go through my conclusion quickly. So I've tried to explain this logical analog of how you talk about optimal approximability and inapproximability for CSPs, and the nice thing is that by restricting, not considering any polynomial time algorithm, but a symmetric polynomial time algorithm, so definable in FPC, we can prove statements without assuming P is not equal to NP. And of course, we still have this unique games conjecture that's open, even in FPC land, but we still have sort of partial results towards that end. And hopefully maybe these ideas could be extended to prove an FPC unique games conjecture more easily than it would be able to be proved in the classical unique games conjecture setting. And finally, I just want to thank Anuj again, who's in the audience, for advising this project while I was at Cambridge. It was very helpful in giving me the tools I needed to solve these problems and helping explain this interesting logical world to me. Thank you.
Okay, well, thank you very much. If everyone wants to unmute for a second to applaud, we'd like to do that. Very, very nice talk. So there were a bunch of questions in the middle. If other people have a few more questions now, that would be good.
Jamie, I just had a couple of questions. Can you go back to the overview of the algorithm?
The construction?
This one.
Yes.
So I basically had two questions. So does that also mean that if you don't do step 5, then is there a winning strategy by spoiler that consists of like, I'm trying to figure, like, what is spoiler's winning strategy? Is it following a chain of dependencies to like sort of restrict to a particular subspace, or is it to close off the tree or something like that?
So the thing that made instance B not satisfiable is that I added all these random vectors. So spoiler's strategy is to try to exhibit a cycle where these random vectors make it where it's clear that there's no way you can to exhibit a cycle where these random vectors make it clear that there weren't the same constraints.
Mm-hmm.
And the step 5 ensures that at some point along that cycle, you're going to hit some path of length R where duplicator is unconstrained and can do whatever they want over that path. And they have some freedom by the fact that by using these subspaces. And because it spans the whole space, they can use whatever the algebraic difference you get in the cycle from all the random vectors is, they can cancel that out by mucking around with the constraints that because it spans the whole space, they can exactly cancel out whatever the effect of all those random vectors were.
Okay, cool. That makes sense. And then the only other question I had was, it seems that so everything you've used is deterministic. So is the only reason for the randomness in step 4 just to bound the number of bad edges?
Yeah, so we tried, yeah, and I know Anuj also tried thinking about this problem of how do you construct an explicit graph with high girth such that you can guarantee that there's no bad edges. And it's really, really hard. We weren't able to do it in any deterministic way. What's nice is that if you just look at, okay, I'm going to start from an edge, and I'm going to count how many bad paths are emanating from that edge, in the sense that how many paths still have failed to span the subspace. And basically, at each step, because the degree is 2 to the L plus 1, you create 2 to the L potentially new bad paths, and each one gets resolved with probability 1 over 2 to the L. And so they kind of cancel each other out. So if you make R big enough, eventually you will get all these paths to terminate, and you'll be good.
Okay, cool. Got it. Yeah, makes sense. Cool.
Okay, I just wanted to maybe ask the obvious question. So it's very nice construction and nice results, and then it looks like you're not that far from proving the more general thing.
I'll tell you how far we are. Is this 1 over 2 to the L is not going to work for us. We really want this to be close to 1, and you could try to generalize this if you made L not an integer, like somebody less than 1, but it really doesn't get you where you want it. But yeah, so the fundamental problem going forward is having a subspace full of constraints on every edge. gives you a lot of freedom. It kind of gets around the uniqueness issue in unique games. And if you look at, but like, for example, this is kind of similar to how, if you're familiar with the 2-to-2 games conjecture, you have 2 constraints instead of 1, and it's the same sort of thing. When the L equals 1, it's a similar idea, and that it gives duplicator the freedom in order to hide the difference between the 2 structures. Because as we know, if you only have, if it's, otherwise duplicator only has 1 move to make. So what we need to do is come up with some more clever ways of, and more complicated graph automorphisms than just every edge has a separate set of automorphisms you can apply on that edge.
Okay. Okay, that gives me some sense. Okay, very nice talk. Is there
I ask one question, which is maybe I just don't know anything about descriptive complexity, but is there some class like FPC, you said doesn't capture things like Gaussian elimination because, is there some class that does capture that and then you can prove non-trivial things for it? Or is this sort of like, and I guess related to unique games conjecture, is there some class that, I don't know, I guess, do you know that if you prove unique games conjecture for FPC, this won't really tell you anything about the polynomial time unique games conjecture, but there's some class that maybe you could use to prove that the full-on unique games conjecture?
So there's these, so there's more powerful logics that fall between FPC and polynomial time that are designed with this intent, where you say, okay, let's like let you solve Gaussian elimination. Right, I think, correct me if I'm misrepresenting the state of the world, but and you can still prove that there are problems that they don't capture polynomial time. It's kind of an open question whether there's a nice natural logic that captures polynomial time over unordered structures.
I see. Okay.
Yeah.
Okay. Cool. Thanks.
right? No, we'd love to know that. And that's there. Right. There's a larger classes that are not exactly logic and don't really have, and you can't really. People don't know how to prove low rounds for.
Yeah, so then it loses its appeal, I guess. Yeah. Okay.
Yeah, but there's similar games. You make the logic more powerful. You make the game more complicated. Like the K-pebble bijective game is already a pretty complicated game. Like if you look at the analogous thing for first order logic, it's very simple. The pebbles just get placed down. They don't get picked back up. There's no bijections writing down. And these more complicated logics have more complicated pebbling games.
I see. Okay. Interesting. Cool. Thanks.
Okay. Well, thank you very much, Jamie. Very good to see you. Enjoyed your talk.